Chapter 11.2b. The question is to block or not to block. Why did our one-way ANOVA tells us there was no difference in the average number of sales calls made by the employees, whereas the randomized block ANOVA confirmed there was a difference? To answer this question, let's investigate the impact of the blocking factor on the hypothesis test. In doing so, we need to decide whether the blocking factor, in this case the weekdays, help or hinder our analysis. Take a look at figure 11.13, which illustrates the partitioning of the sum of square or SST for both the one-way and randomized block ANOVA. With a one-way ANOVA, we will have a greater chance of rejecting the null hypothesis when more variation in the data is due to the SSB rather than the SSW. Notice in figure 11.13, with a randomized block ANOVA, the SSW is further partitioned into the SSBL and the SSE. A small variation in the data is explained by the SSBL for given values of K and B. So 1, less is attributed to the SSE. 2, which make the MSE equal to SSE divided by B minus 1 times K minus 1 is smaller. 3, which make the test statistic or Fx equal to MSB divided by MSE larger. 4, which increases the likelihood of rejecting the null hypothesis when F statistic greater than F alpha. To illustrate this point, take a look at table 11.20, which compares these two ANOVA using the sales call example. As you can see, the test statistic for the randomized block ANOVA has a smaller denominator, 0.85, than the one-way ANOVA, 2.27, because the block factors weekdays has removed some of the variation. In this example, the blocking factors was effective because it resulted in rejecting the null hypothesis. In other words, we were able to tell that the days of the week were masking the result, that the representative weren't really making the same number of calls per week. When the blocking was not used in our one-way ANOVA calculation, we did not detect a difference in sales call and failed to reject the null hypothesis. We can take this question of whether to block one step further by testing the significance of the blocking factors. With our sales call example, we have the following hypothesis. Null hypothesis, MBL1 equal to MBL2 equal to MBL3 equal to MBL4 equal to MBL5. Alternative hypothesis, not all MBLS are equals, where MBLI is the population mean for the ith block. There are 5 means in this null hypothesis because there are 5 blocks in the sales call example, Monday to Friday. The blocking factor test statistic for the randomized block ANOVA is used to determine if a difference in block means exists. It is shown in equation 11.18. As we'll see later in this chapter, this information can help us decide if the blocking factor was useful in the analysis. Using our square values from figure 11.12c, the calculated F-score for the blocking factor, FBL, is as follows. FBL is equal to MSBL divided by MSE equal to 5.1 divided by 0.85 equal to 6. The blocking factors test statistics shown in figure 11.18 follows the F distribution with the following degree of freedom. D1 equal to B minus 1, D2 equal to B minus 1 times K minus 1. Using our sales call data, the blocking degrees of freedom are as follows. D1 is equal to B minus 1 equal to 5 minus 1 equal to 4. D2, B minus 1 times K minus 1 equal to 5 minus 1 times 3 minus 1 equal to 8. According to table 11.8, the blocking critical value for our sales call ANOVA using alpha equal to 0.05 and degrees of freedom equal to 4 and 8 is F alpha equal to 3.88. Because FBL equal to 6 is greater than the F alpha equal to 3.838, we reject the null hypothesis according to the decision rules shown in table 11.9. By rejecting the blocking null hypothesis, we have evidence that the blocking factor was effective and that it belongs in our final analysis. In terms of the sales call example, this conclusion means that the weekdays appear to influence the number of sales calls made. This can also be verified by looking back at figure 11.12c and observing that the p-value for the blocking factor found in cell K17 is equal to 0.056, which is less than alpha equal to 0.05. In other words, in some weekdays, there is a higher or lower number of sales calls across all three employees. This is why we fail to reject the null hypothesis for the sales call example using a one-way ANOVA, and we able to reject the null hypothesis using randomized block ANOVA. We have a note of caution at this point. If one of the objectives of the ANOVA procedure is to test specifically for a difference in the mean of the block, that is, if the goal is to consider the block as a main factor, the randomized block ANOVA would not be the appropriate procedure. Rather, the two-way ANOVA test, which is discussed later in the chapter, would be the procedure of choice. The ANOVA table for the randomized block procedure, which is shown in table 11.21, look slightly different from that for the one-way ANOVA example. Table 11.22 summarizes the result of the sales call randomized block ANOVA. If you decide to use the randomized block ANOVA and fail to reject the null hypothesis for the main factor, it's important to investigate the effectiveness of the blocks by looking at the p-value for the rows source of variation in Excel. If blocking is not effective, it will result in your failing to reject the null hypothesis for the blocking factors. So, including it in the final analysis could result in inflating the probability of a type 2 error or failing to find a difference in the mean when one really exists. In a sense, the blocking factor, because it is ineffective, is masking the true difference in the mean of the main factors. In this case, you should redo the analysis by conducting a one-way ANOVA. The following is a quick example. A certain unnamed statistic author likes to humiliate himself on a regular basis by playing golf with his two sons. who like to remind him constantly how much better they are on the golf course than he is, in spite of the fact that he always pays for the round. To investigate this claim, they recorded the last 4 rounds of golf play by all 3 players at 4 different courses. The scores are shown in Table 11.23. Because each row in Table 11.23 represents a different golf course, a randomized block ANOVA would appear to be the analysis of choice. Figure 11.14 shows the result using Excel. Because the p-value for the main factor or golfer in cell K17 is 0.087508 and is greater than alpha equal to 0.05, we fail to reject the null hypothesis. In other words, there is no evidence to support the claim that the Suns are better golfers than their poor broke dad. However, because we use a randomized block ANOVA and fail to reject the null hypothesis, there is a chance that the blocking factor is masking any true difference in the main factor means. Figure 11.14 provides us with some evidence that the blocking factor was not effective in this analysis. The p-value for the blocking factor or course can be found in cell K16 and is equal to 0.964384. Because this value is greater than alpha equal to 0.05, we fail to reject the null hypothesis, which means the blocking factors is not carrying its weight in the problem and should be removed from the analysis. In fact, you look at the average score in cell 14 through 17, you will see that the different courses don't have much effect on the score of the golfer. Thus, the blocking factors is ineffective. To do the analysis properly, we should perform a one-way ANOVA to be sure the blocking factors is not covering up the difference between the golfer's average score. Figure 11.15 shows the one-way ANOVA result from Excel for the golf score example. Notice that the p-value in cell K12 is now equal to 0.02878, which is less than alpha equal to 0.05. Our final conclusion to this case is to reject the null hypothesis for the main factor. It appears that there is a difference in the average golf score of these 3 players. To spare his pride, it looked like this author needs to keep this chapter away from his son. Use the following step as a guide to answer the question to block or not to block. 1. If a blocking factor seems appropriate for a particular analysis, begin with a randomized block design. 2. If the main factor is significant, reject the null hypothesis and proceed with your conclusion. If the main factor with the randomized block design is not significant, proceed to test the main factor with one-way ANOVA design. As long as the main factor is statistically significant, there is no concern about the significance of the blocking factors. Remember, the purpose of using the randomized block design is to reduce the variability due to the blocking factors. If there is an interest in investigating the significance of the blocking factors, the randomized block ANOVA is not the appropriate design. Rather, a two-way ANOVA design, which can test the significance of 2 main factors, should be employed. We'll discuss the two-way ANOVA procedure later in this chapter. Table 11.24 provides a summary of the steps required to test the main factor using a randomized block ANOVA design. 1. Identify the null and alternative hypothesis. 2. Calculate the factors mean, the block mean, and the grand mean. 3. Calculate the total sum of square. 4. Partition the total sum of square SST into the sum square of between, the sum square of block or SSBL, and the sum square of error or ASE. Calculate the corresponding mean square. 5. Calculate the main factor test statistic. 6. Determine the appropriate critical value. 7. Compare the F-test statistic or Fx with the critical F-score or F-alpha. 8. State your conclusion. Multiple comparison. Comparing pair of population mean or randomized block ANOVA. There are several different procedures to choose from when asking multiple comparison for a randomized block ANOVA. We'll demonstrate the Taki-Kramer multiple comparison. Test for randomized block ANOVA using the PNG sales call example. This procedure is very similar to the one-way procedure discussed earlier in the chapter when we were looking at the smartphone data. Step 1. Calculate the absolute sample mean differences. With k equal 3 population or employees being compared, we have 3 times 2 divided by 2 equal to 3 pairs of samples mean. The pairs are made up of the following samples. We compare between 1 and 2, 1 and 3, and 2 and 3. Using data from table 11.16, we have the following. X1 bar minus X2 bar equal to 5 minus 7 equal to minus 2. Absolute value is 2. X1 bar minus X3 bar is equal to 5 minus 5.4 is equal to minus 0.4, absolute value 0.4. X2 bar minus X3 bar equal to 7 minus 5.4 equal to 1.6. Absolute value is 1.6. Step 2. Calculate the critical range. The critical range for comparing pair for a randomized block ANOVA or CR is used to determine if the difference between a pair of sample means is large enough to conclude that the population mean are significantly different. The formula for CR for a randomized block ANOVA is shown in figure 11.19, where CR equal to the critical range for comparing two sample mean. QA is equal to the critical value for the studentized range table, Appendix A, Table 7. MSE, the mean square error. B is the number of blocks. The critical value QA is found in Table 7 in Appendix A. The value is based on our desired significant level and the following two degree of freedom. D1 equal to K, D2 equal to B minus 1 times K minus 1. Using the PNG sales call data with K equal 3 employees and B equal to 5 weekdays, the degree of freedom are as follows. D1 is equal to K equal to 3, D2 is B minus 1 times K minus 1 equal to 5 minus 1 times 3 minus 1 equal to 8. Using table 7 in Appendix A with alpha equal to 0.05, the critical value is QR equal to 4.04. The critical range for the P&G sales call example can be found with equation 11.19. Recall that from table 11.22 that the MSE equal to 0.85. So CR is equal to 4 times 4 times square root of 0.85 divided by 4 is equal to 1.67. Step 3. State your conclusion. We can use the decision rule in table 11.13 to determine which pair of population mean are different. Table 11.25 shows this decision rule being applied to the 3 pair of sample. So X1 with X2, their mean are different. X1 with X3, the mean are not different. X2 and X3 means are not different. The average number of weekly sales call made by Dan, or 1 with Amy, or 2, there is no evidence that the other 2 pair, Dan and Beth and Amy and Beth, have different mean based on this data. Thank you.